So now we're going to talk about inference testing. And if there's only one thing you ever get for Christmas, I really hope it's to understand what a t-test is. And to prove how much I desire that you learn this, I brought some Justin Bieber Christmas. A t-test. That is my wish for you, is that you understand inference testing and a t-test. So the way we're going to set this up is we know that we have population parameters. So our population parameters is the population mean, which is mu, the variance, which is sigma squared, and even the standard deviation, which is just the square root of the variance, which is just sigma. And if we knew this, life would be grand, but oftentimes we don't know the population parameters. So what we do is we look at our sample, and we have our sample parameters. So we have our sample mean, which is x bar. We have our sample variance, which is s squared. And we have our sample standard deviation, which is just equal to s. Okay? And so this is what we want to think about from this. Okay? And what we want is to be able to get our sample and to be able to do tests to see if it actually equals our population. Okay, so to do this, we want to first, let's define what these are. So x bar is equal to 1 over n, summation of xi. You just add up all the x's, divide by n. S squared is a little crazier. It's 1 over n minus 1, summation of xi minus x bar squared. And s is just that whole thing, the square root. We also want to add the term of standard error. And the standard error is equal to s squared divided by square root of n. All right, so this whole thing divided by the square root of n. So these are sample parameters, things that we estimate. And we want to be able to test to see if they're close to what we might think of as the population. All right, so when we do this, what we want to think about is creating a null hypothesis. All right, and our null hypothesis is H sub naught, the hypothesis null. And we want to think about this as some estimate that we have. Think of x bar is equal to some population parameter. Then we have our alternative hypothesis, that x bar doesn't equal, oops, not that population parameter, let's use mu, doesn't equal our population parameter. And that's what we want to do. So what we want to think about is our population parameter, mu, has a distribution. Okay? So think of this as a distribution. So here is mu, and we want to estimate where we end up. We want to estimate where our parameter is. So within this, where our sample parameter is. So within this, we want to create what we call a critical region. All right? So we want to think about how close to mu do I have to be for me to be happy enough. So if x bar is right here, that's really close to mu. I can live with that. And I can say, yeah, that's close enough to mu that I can think that's the same as mu. But if x bar is way out here, I don't know if that's close enough for me. So what we have is what we're going to use is t-tests, which is a type of an inference test. So a t-test is based off this comparing our sample to a population parameter. All right, so we're going to establish an alpha. All right, and alpha corresponds directly with the significance level. All right, so if I want a significance level of 95%, meaning I want to be 95% sure that when I reject the null, that I'm actually doing it correctly. All right, and so as a result, I want 5% of my data to be out here in the tails. So that means my alpha is going to be 0.05, because 95%, the difference is going to be there. So for 95%, I want to, and we're going to focus on what's called a two-tailed test, is I want my data, this range here, to be 95% of all data points within this range. And that means these tails here is what's left over. Now, because the t-distribution is symmetric, this means that this is going to be 0.05 divided by 2, which is 0.025. And this is also going to be 0.05 divided by 2. So that's what we have in terms of here. So if our data, if our estimate falls within this area, we call this area right here and right here a rejection region. So if it falls within there, we're going to reject. Now, if I were to look at the back of a table, I could see that based on these alphas, there's some number here that's going to correspond to that. All right, so if I'm thinking of a two-tailed test, this number is going to be 1.96 and negative 1.96. Hold on, let me check on that. That doesn't seem right. So let me pull up my book real quick to show you what we're talking about, if I have one. All right, so I'm going to pull up the back of my stats book that I use as an undergrad. Just want to make sure we get these numbers right. And I'm going to look at my t-statistic. Not a chi-squared. Here's my student t-statistic. So I'm going to look at, I want the area to be 0.025. So if I come down here, oh, I can't even see it. What you'll see is all the way down here. So I'm going to start at 0.975. It's going to be 1.96. So we did get it right. Sweet. All right, so that means 95% of my data is here, and 0.2025 is here, and 0.025 is there. All right, so that's how I set up my t-test. Now the question is, when do I know to reject? Well, I set up my null hypothesis. Before I have is x bar is mu. So my t-stat is equal to x bar minus mu over the standard error of x bar. And that's going to give me a t-statistic. And that t-statistic I'm going to compare to see if it falls to the left here, if this is where my t-stat is, then I fail to reject and conclude that that's close enough to the population parameter that I imposed. But if it falls over here, then I reject the null, which is that x bar is equal to mu, and say that x bar is different than mu, that I don't actually have the true population parameter here. And so that's how we're going to do a t-statistic. Now, if you have more questions on this, you really need to look at what's going on back in Stata, or sorry, what's going on in your stats class. So there is a lot of notes on this, so go through a little more detail, but this is what we're thinking of in terms of our t-statistics that we're going to be testing here in Excel.